So hi everyone, and thank you for joining us in this session. Welcome to AI for Signals track. My name is Itai Buchnik. I'm an AI researcher at Elbit Systems, the largest defense company in Israel. To be more specific, I'm a part of a big R&D group in the ISTAR and EW division, ISTAR, located in Holon. Our focus is to develop algorithms and utilize AI techniques to extract intelligence from electronic signals. This is why we host this track together with AI Week. In the next hour and a half, we will dive into a number of problems in this fascinating field and invite whoever is also passionate about signal processing and AI to reach out for any possible research cooperation. So, what types of signals are we talking about in this session? The 5 amazing speakers will present their work regarding signals that can be divided into 2 groups. In the first group, electronic signals that were made and designed by engineers, for example, radar or communication signals. The second group are natural signals that were collected by sensors that are designed by engineers. For example, acoustic signal or body measurements, air measurements like temperature. The exciting challenges in AI for signals is, first of all, the data. As you can see, we have in the left side so many public data sets and benchmarks related to vision or language, but very few in signals, and almost none in electronic signals. Second is lack of research in the field. For example, we have a lot of research invested in generating images, but good luck finding a really good paper that can generate a valid communication signal using AI. Many foundation models exist for different domains, and many papers explain how to do self-supervision in language. But how can we really perform self-supervision with signals? Does it exist somewhere? Maybe here in the crowd someone can help us? We have a diverse and special track full of inspiration. I'm excited to invite the first speaker, Dr. Nir Shlezinger, from the School of Electrical and Computer Engineering at Ben-Gurion University, that will talk about data-driven Kalman filters.
So, yes, these are my slides. Let's see that this one also works. Yes, it does. Okay, guys, thank you very much for coming. It's a great pleasure to be here. Thanks, Itai, for the introduction. Thank Viv for inviting me, and thank you guys for being here in this very interesting venue about AI and signal processing. So my talk is entitled Data-Driven Kalman Filters, but I will actually start with more of my perspective, which I believe many of us share, on how AI should be combined with signal processing. So obviously, we're here in AI Week. We're familiar with how machine learning is successful, and we all like to think that this idea of AI, which is based on machine learning, namely algorithms that learn their operation from data, is a new concept. We think it's something that popped up in 2012 with AlexNet, but the whole idea of having machine learning models that imitate the operation of the human brain is actually quite old. It's over a century old, dating back to the Pitts McAuliffe ideas from the 1940s, but we're currently witnessing how it's revolutionizing so many fields that we're working with. And honestly, if we're actually in the day where our coffee machine effectively beats us in any data science competition, if our coffee machine can interface with ChatGPT, it already does. Now, specifically, the form of machine learning where we're witnessing the greatest success stories are those of deep learning, namely where the machine learning models that we are working with are trying to imitate the operation of the human brain using models based on deep neural networks. And here we're seeing the dramatic success of AI, particularly in the areas of computer vision and natural language processing. But for us as signal processing researchers looking at this, we can say for a fact that these are the kinds of problems which before deep learning, we didn't have sufficiently sophisticated tools to deal with because there were problems that didn't have very good statistical models. No, but there are a lot of areas in which there are statistical models that describe the underlying problem. For instance, signal processing is often governed by physics, like Itai presented earlier. A lot of signals, such as communication signals, radar signals, are ones where whose properties can be characterized mathematically through a statistical model. And we have established models in many applications. When I'm saying models, I mean statistical models, not deep learning models. In signal processing, in communications, in control. And if we have a good statistical model describing the problem, we usually also have a good algorithm. However, if we're citing famous statistician George Box, well, all models are wrong, but some are useful. So the thing is that the models that we have are all approximations of the real world. When they are inaccurate, then our algorithms fail. When they are accurate, well, assuming that they're also sufficiently simple, we can get pretty good algorithms in signal processing. Okay, so maybe let's further capitalize on the difference between deep learning as we see it and model-based methods that are based on statistical models. Let's look on the example which is the focus of today's talk, tracking of dynamic systems. Tracking of dynamic systems, that's a fundamental task in signal processing. It's essentially about tracking a state variable from noisy measurements. That sounds very abstract, but it represents a lot of tasks like localization, navigation, radar tracking, vehicular control. All of those applications involve noisy measurements based on which one has to track a state that evolves in time. And, well, this is not a new problem, right? In signal processing, we're familiar with this. And actually, Rudolf Kalman looked at this problem back in the late 60s, early 60s, sorry, and proposed a celebrated algorithm called the Kalman filter. And the Kalman filter became very famous. And this is Rudolf Kalman, the Hungarian mathematician, being awarded the Medal of Science from President Barack Obama for his discovery of the Kalman filter, which is an algorithm for tracking dynamic system. And it has become very famous when it was discovered or identified by NASA researchers as being useful for tracking the trajectory of the spacecraft, and it was incorporated in the Apollo program that successfully landed the first human on the moon. However, as Rudolf Kalman was a mathematician, this is based on the ability to describe our problem using a statistical model, and I will discuss about this later. And obviously, when we have a good knowledge of the dynamics, it works, and when we don't, these algorithms fail. Now, obviously, we don't have to rely on modeling. We can rely on data. If we have a lot of data describing the trajectory of the spacecraft and the resulting measurements, we can design data-driven approaches based on machine learning, on deep learning, for instance. If these are time sequences, it makes some sense to use recurrent neural networks, transformers, recent Mambas, any one of those architectures which are suitable for data-driven applications. But then again, once we go into the deep learning domains, we lose a lot in terms of interpretability. Generalization also becomes a hazard. We talked about a lot of hallucinations earlier. And obviously, training these things is a hazard on its own. Now, this leads to trying to find some kind of golden path between. Because we know that if we have algorithms that rely on data, they have their own pros and cons. And if you have algorithms that rely on statistical modelings, they have their own pros and cons. And, well, if you want to take a take-home from my message is that in signal processing, we often have both. So while Itai said we don't have a lot of data, we can compensate for that because we have a lot of knowledge. And that leads to hybrid techniques that combine both principled mathematical models and data-driven systems. And this is what we call model-based deep learning. Let's go a bit more specific. If we want to look at a classic, a model-based design of a signal processing algorithm, let's say it's a tracking of dynamic system, it's a Kalman filter, we would have an algorithm which is based on our characterization of a statistical model. Obviously, this statistical model has its own parameters, so we usually identify its parameters from data using measurements, using simulators, and so on, and we just substitute it into the system. A data-driven approach, at least based on deep learning, would use an abstract solver, which is essentially good for all tasks, and would use data in order to feed it to the current tasks without incorporating any domain knowledge into it. The algorithm-driven approach, which is what we're advocating, is somewhere in the middle. It takes the model-based approach, but instead of trying to estimate the statistical model, it tries to convert the algorithm into a machine learning method. So in terms of the machine learning terminology, the classic approach would actually be a form of generative learning because data is used to learn the underlying statistical model. The data-driven approach would be more of a discriminative learning. And what we're trying to propose here is to convert classic algorithms into trainable discriminative machine learning models. So in the context of the Kalman filter, Well, now I pressed the wrong button. Okay, so in the context of a Kalman filter, the model-based design would be the Kalman filter, the data-driven one would be the recurrent neural network, and the hybrid design would be Kalmanet that I propose shortly. Now, this is an area that we're extensively working on. We have several overview papers, a recent monograph on that area, and it's essentially about trying to enjoy the best of both worlds, focusing on domains such as signal processing, communications, and control, where we have good statistical models. So let's go specifically into Kalman. So I said that the algorithm developed by Rudolf Kalman relies on the ability to represent the dynamics using a statistical model, and the statistical model is one which relates observations denoted Y and an underlying state denoted X using a state space model. It essentially means that the state that we do not observe evolves as a Markovian process, and we're observing it using some noisy measurements. Now, this model is actually quite accurate in many cases. For instance, let's say that we want to track a moving object. Then, well, it makes a lot of sense to say that its position and velocity at time t would be its position at time t would be its position at time t minus 1 plus delta t times the velocity. That makes a lot of sense. However, everything that we don't know, and there's a lot of it, we just throw and model it as noise. So if our modeling is inaccurate, that's a limiting factor. Now, Rudolf Kalman looked at this problem and one which is a bit simpler, where the transformations are linear and Gaussian. And for this problem, he proposed the filtering algorithm coined the Kalman filter, which is not only very simple, its complexity does not grow with time because it uses the previous estimate as a sufficient statistic for estimating the next state. And it essentially is based on two steps. Broadly speaking, there's a step which takes the previous estimate to predict the next observation and the next state, and another step which takes this, the current observation and balances it with the prediction based on this matrix that is called the Kalman filter. So it looks like a sophisticated block diagram, but it's just predicting based on the previous estimate and a lot of computation based on the statistical moments of the noise signals, which allow you to compute the Kalman gain and to balance them. Now, as I said earlier, often we do have a good model for the dynamics. They're relatively reliable first-order approximations. The noise signals is usually something that we just kind of impose on the model. And as we saw earlier, actually the part of the Kalman filter computation which depends on all these unknown parameters is the computation of the Kalman gain. So what we proposed to do was, instead of replacing the Kalman filter with a deep neural network, or essentially trying to estimate the parameters of the state space model, impose Gaussianity and estimate these parameters, simply convert the Kalman filter into a machine learning model by augmenting the computation of the Kalman gain with a recurrent neural network. Why would that work? What are the gains we're getting out of it? Why would we like to convert the Kalman filter into a machine learning model? Well, first, if we compare it to the extended Kalman filter, the one which relies on knowledge of the dynamics, then obviously we're model agnostic. So we're capable of coping with mismatches because you learn from data. So you get a better performance. And also recall that the extended Kalman filter on its own is not optimal, so you can cope with non-linearities that way. But there are also other gains. If you compare it to black box approaches based on recurrent neural networks, it generalizes much better, simply because what it learns to do is implement the Kalman filter. Now, it's not only in terms of accuracy, you can also gain performance in terms of inference time. Because if you think about it, the extended Kalman filter on each time step has to linearize the state space model, invert a matrix. These computations can be quite lengthy. And what we saw is that instead of replacing these computations with a trainable model, can actually make it operate faster in many situations. Of course, it's much faster compared to black box deep learning models. Now, the gains of this approach are not only in performance. Okay? You can also get concrete gains by the fact that it's interpretable. Because one can say, okay, I'll just put a strong transformer, I'll get very good performance, and I don't care about latency. However, if we do preserve the operation of the Kalman filter, we get a lot of gains. For once, we saw that you can implement it on very simple hardware. We implemented this algorithm on the on the limited vehicle control unit of an autonomous racing car, where they didn't successfully implement previously any form of deep learning models because they couldn't make it run fast enough as they wanted. They needed 300 velocity estimates a second, and we managed to get it to work. We were awarded the first AI prize, but the car didn't win the race. So we blame it on the mechanics people. Another gain that you get, think about it, the Kalman filter on its own not only tracks the state, it also tracks the error covariance. So this is something that is very hard to do in deep learning, right? getting a reliable form of uncertainty in deep learning is very challenging. People do Bayesian deep learning to do that. Here you get it for free because you preserve the operation of the Kalman filter. Another thing that you get because you understand what actually goes on under the hood, one of the features that the Kalman filter computes is the next observation. We can use it to train. That allows us to train this thing unsupervised, which is not that simple to do. And also, a lot of us already have implementations of Kalman filters that are working on our systems. It's very simple to convert and to augment them using this kind of methodology instead of completely replacing it with some transformer or other form of deep learning model. Another form of gain that you get because you converted the Kalman filter into a machine learning model stems from the fact that you no longer have to separate its design from the rest of your system. For instance, often we are applying Kalman filter on top of some extracted features. Let's say we have an image. Our image, we have some visual data. From the visual data, we get an estimate, and we feed it to the Kalman filter. Now, if we have a trainable Kalman filter, we can jointly train the Kalman filter alongside the feature extraction and get the features that are most useful for training using our learned Kalman. We can also use that, for instance, if we have graph signals, we can do this conversion to the graph signal domain and make this processing much more efficient. If you guys happen to recognize the name Buchnik here on the first place, it's because it's our humble moderator here sitting in the first row. We can also combine the operation with some downstream tasks because Kalman filter is often employed in conjunction with some downstream tasks in control. We also implemented it in finance for tracking stocks. It worked very well. We didn't get rich, but we published a paper, which is nice. We implemented it for brain-machine interface for tracking neural signals. So what I'm trying to convince you guys is that by converting your Kalman filter into a machine learning model, you actually get the best of both worlds, both the deep learning model world and the data-driven one. And I will conclude with thanks to my awesome students and past students who've been doing all the hard work. I'm just talking. Amit, Itai, Jonathan, Guy, William, and my awesome collaborators, Tirza, Rud, and Yonina. And thank to you guys. Thank you very much.
Thank you so much, Nir, for still being my inspiration from my master's to today. Any questions for Nir in the audience? Yes. Over there, Amit.
I recall from my studies that if Kalman filter is not good enough, you don't go to extended, which is considered bad, but you go to unscented, and if it's not enough, you go to particle filter. So how it's compared to these ones?
Very good point. Okay, so this is a very signal processing question. Yes, if you have a nonlinear state space model, the extended Kalman filter is one option. You have the unscented Kalman filter, which propagates the second order moment slightly differently. Okay, what we're doing here, we're bypassing the need to propagate second order moments. We actually saw that it works better, the unscented one. Particle filters are a whole new domain. This is something that we are also working on. But particle filters are also much more complex, and their performance highly depends on how much particles you're using. So based on the settings that we experimented, we managed to get better performance compared to both, and they both still rely on your ability to fully characterize the underlying state space model. We kind of bypass this by doing this approach.
More questions? Yeah, Amit.
Thank you. Can you explain how you constrain the RNN to perform like a Kalman filter?
Well, what we actually do is we train if you look at the architecture, this one, it actually is supposed to output a Kalman gain, right? But there's no ground truth Kalman gain. If I don't have a good state space model, I don't have a ground truth Kalman gain. And even if I do have, and it's non-linear, it's non-Gaussian, I don't have a ground truth Kalman gain. But what we do, we train it as a discriminative model, and we train the output to be an estimate of the state. And we also showed that you can train the internal feature which maps the next observation to just predict the next observation. Is it really the ground truth Kalman gain that you end up? What we showed is that for scenarios where it is, you actually get that empirically without having to regularize the system to get it. But for scenarios where one does not exist, we can only observe this guy. We can only observe performance.
But that's very interesting if it just naturally evolves, don't you think?
Well, it actually makes a lot of sense, right? Because the Kalman filter is the minimum mean squared error estimator for linear Gaussian state space models. So it would make a lot of sense that we would manage to learn this specific mapping. I would say that in scenarios where there's not necessarily just, a grooved Kalman gain, that would be even more challenging. So the way I see it, the fact that we managed to do so is not surprising. I would have been surprised if we wouldn't have managed to learn that. The more challenging cases are the ones where there's no real common gain.
I'm sorry to stop the questions. We need to move on. But after that, you can ask Nir thousands of questions. So let's thank again Nir for this talk.